Okay, so welcome to Math 317. It doesn't look like it's showing the screen. Oh well. All right, so welcome to Math 317, Operations Research. This should be lecture 25. And what I want to do today is talk about some of the analysis we need for the fixed point theorem we want to prove. So again, there's a lot of different fixed point theorems that you can prove. They have different applications, different uses. What I want to do is I want to focus on what was needed for the Bauer fixed point theorem. So we already talked last time, and this is the advantage of having everything on the iPad rather than on the board. I can just quickly scroll back to, all right, so what did we do last time? So we started off by talking about how if we change coordinate systems, we can often make one region equivalent to another through a well-defined map, often a map that has a lot of nice properties. And thus, instead of studying a general space, it's frequently enough to study a specific space and then somehow pull it back to whatever you want to look at. So in Math 150, you should have seen lots of examples of this through your Cartesian to polar or Cartesian to spherical, getting nice boxes that are easy to work with. So we talked about how you will not always have a fixed point. Continuity is an absolutely essential constraint. We also saw that needed to be bounded. We talked about how if we just move the entire plane by one unit, there'll clearly be no fixed point. We talked about puncturing a unit circle and missing the center. Now you won't have a fixed point. You can just rotate it by something less than 360 and greater than 0. So all these conditions are necessary. The further you go in analysis, the more difficult it can be. And the best advice I can give you is the advice Professor Jones gave me at Yale. Always take your theorems, remove a condition, and you should either be able to find a counterexample or the proof should be a lot harder. So we then quickly talked about the different spaces we're going to look at, essentially line, triangle, tetrahedron, generalized tetrahedron. I don't know what they're called. And if we can just prove it in this setting, everything is good. All right. We then talked explicitly about how if we have a fixed point in maps from T to T, and T and S are nicely related, then that gives us fixed points of the associated map from S to S. So really, we only have to understand one nice space, and then we can understand anything equivalent to it. All right. So the rest was then just going through and showing how you would find the fixed point if you know it from the function from one space to the other to the connecting map. Okay. And then we talked about then, how can we apply this and use Sperner's fixed point theorem? Well, what we did is we talked about how if we have a map with these barycenter coordinates, it's really nice. The coordinates are all going to be numbers between 0 and 1, and the sum is going to be 1. So if there's no fixed point, then that means when you apply your function f to your point, say x0, x1, x2, then you will have to get some new point x0 prime, x1 prime, x2 prime, where all of these are distinct from the initial. So if they're all distinct, at least one of them has to be the first one where you have something smaller or the first one where you have something larger. Doesn't really matter which way you do it. We eventually thought about it and we said, well, we want to use Sperner's lemma. So let's define the index function to be the first place where your index is lower. I'm sorry. Yes, it's lower than what you initially started with. So is x0 prime less than x0? If yes, then the index is 1. The index is 0. If x1 prime, if 1 is the first index where it's lower, then 1 would be the value of the index function. And by choosing it like this, we see on our triangle, it's going to be labeled 0 in the bottom left, 1 in the bottom right, 2 up on the vertex, and the sides are going to be exactly as we need for Sperner's lemma. And under the assumption that there are no fixed points, if we keep triangulating, and then at each point of the triangulation, if we then put the value of the index function, we will have a labeling of these points with 0, 1s, and 2s. And so what does Sperner tell us? So we'll have these triangulations, and we'll have small and smaller meshes. Each triangle will be labeled with a 0, 1, or a 2. What must be true about the final labeling? Good, there must be some triangle with a 0, 1, or 2. We talked about how we would love it if we could say, well, let's say initially this was the triangle that had the 0, 1, 2. Let's zoom in on that. Why can't we do that? Why can't we just say, well, okay, now we have a triangle with 0, 1, 2. Let's play the game again, but starting with this triangle. Right, we don't know the edges satisfy. So a really good question, which you should have all been thinking about, is what if I give you, say, something very similar where I labeled the corners 0, 1, 2, but I dropped the requirement? Does that mean I now have to have a 0, 1, 2 triangle? What do you think? So what should you be doing as soon as I ask a question like this? How would you get some idea of what the answer might be? Try it, right? So for example, let's take something like this. Let's put a label of 0, 1, 2. How many divisions do you want to make things nice? What's the easiest thing we could try? Okay, so how many more? So put in 3 more vertices. And let's think about how we could label. All right, so any thoughts for how we should label vertices, A, B, and C? Yeah, if you label them all the same, I was thinking of all 2s, put all the same number, and then the only chance you would have, can't be coming from the 2 up here, but nope. Each of these triangles is always going to have at least 2 vertices that are the same. So we immediately see it's not necessarily the case that you will have a triangle labeled 0, 1, 2 if the initial boundary conditions fail. Those conditions are absolutely essential. There is no chance that we can make this argument of zooming in, zooming in, zooming in work. We're going to get a sequence of triangles all over the place. But again, you want to get in this mindset when you're doing anything in analysis. You have a result, we move a condition, is it still true? Sometimes the conditions are deliberately designed to mislead you. Does anybody know what a red herring is? What's a red herring?
It's like a fake clue that you think.
Right, it's something that's completely irrelevant to the problem, often designed to deliberately mislead you. A lot of times on exams, there are red herrings, information that just doesn't matter. It's good to be aware of them because when you're doing things in the real world, you will often have a lot more information than you need. And you have to figure out which information is actually relevant. And so when you're doing something like this, try removing a condition. Sometimes by having a condition available, it might focus you on proving something in a certain way that might work for that problem, but it may not generalize. And so it could actually work for that specific problem, but not as you go further. Or it might make you start attacking it in one way, and there might be a simpler way available, which you might not see because you're using some information that's in the problem. I have a great example of a problem like that that I will give at this time at the end of today. All right, so let's talk about the analysis we need. So we need the Bolzano-Weierstrass scale. So let us be a compact set. That means a set that's closed and bounded. So closed means if you have any sequence of points in the set, then a subsequence converges in that set. All right. So for us, oh wait, that's what we're proving here. Sorry. For us, closed means if you have any sequence of points in the set that converges, it converges to something in the set. So if I give you, so closed, so xn in set, xn converges to x, then x is in set. And bounded, it exists in R greater than 0, such that for all x in set, the absolute value of x is less than R. Okay. So we're not going to talk about the most general space possible. Think of something as it lives inside a giant ball. some ball in Euclidean space, some number of copies of R. And by closed, think of it as it includes the boundary. So not a dotted circle, all the values, x squared plus y squared plus z squared, strictly less than 1, x squared plus y squared plus z squared, less than or equal to 1. And what we want to prove is that if I give you any sequence of points, then there's a subsequence that converges. So let's do the proof for S, the interval 0, 1, and then we'll talk about how we can generalize. So again, we'll try one of the simplest cases possible. I have the closed unit interval. As an aside, I've been talking about if you remove a condition, it should either be false or hard to prove. Imagine I gave you the open interval 0, 1, so it doesn't include the endpoints. Can you give me a sequence in the open interval 0, 1 that converges, but does not converge to a point in the open interval? So if you take the open interval 0, 1, you give me a sequence of points in the open interval that converges to something, but that something is not in the interval 0, 1. Yeah, xn equals 1 over n. If open, take xn equals 1 over n, converges to 0, which is not in the interval 0, 1. So we can see that it's essential that we include the endpoints. Otherwise, I can give you a sequence of points in S that has no subsequence converging to something in S. Because any subsequence of 1 over n is still going to converge to 0. Is everybody comfortable with this? Okay, so here's the proof. Let's take the interval 0, 1, and let's split it in half. I claim that in at least one of those two intervals, there have to be infinitely many points of the sequence. Why? So why must that be true? What would happen if both intervals only had finitely many points of our sequence?
Then it's possible that some combination converge.
Well, what are we assuming about our sequence? What do I tell you initially? We have, well, the set S is closed and bounded. We have a sequence xn, n goes from 1 to infinity, is a sequence of points in S. Imagine there are only finitely many terms of the sequence in the first half, and there's only finitely many terms in the second half. One half is in both. What would it mean if there's only finitely many in the first half and only finitely many in the second half? I mean, the sequence of points is finite. But we know there's infinitely many points in the sequence. So at least one of the two intervals has to have infinitely many. Okay. Choose the smallest n in the first with infinitely many points. Call that, say, xn1. So for instance, let's assume this is the one that has infinitely many points, and then maybe over here, this would be the point xn1. Okay. All right. Now it's shampoo mathematics. Lather, rinse, repeat. So now we focus on the interval 1/2 to 1. We have over here the point xn1. What do you think we do now?
Find xn2.
Okay, so how are we going to find xn2?
Just follow the pattern of the sequence of the next n.
Okay, but how do I do that?
We have to know the sequence.
Right, so we don't know the secrets, we're working in general. So what we did in the first step is we took the interval 0, 1, we cut it in half, we said one of the two subintervals had to have infinitely many points, choose the smallest n, and make that xn1. So what do you think we should do here? So what should we do? Cut it in half, right? Lather, rinse, repeat. Take what we did, do it again. So let's cut this in half. So we'll put this in now at 3/4. And one of them, 1/2 to 3/4, or 3/4 to 1, has infinitely many. Choose first with infinitely many. Choose smallest n greater than n1 to be n2. And so maybe there were infinitely many in this part over here, and maybe here's xn2. And so we keep doing this. Every time we do it, we cut things in half. So we get a sequence xn1, xn2, xn3, ... And what's the distance between xnk and xnk plus 1? It's less than equal to how much? So how close, for instance, are xn1 and xn2? They're a quarter. The worst case would be is if xn1 is 3/4 and xn2 is 1/2. So when k equals 1, or maybe here, this will probably be a better way to do it. Let's do it this way. Let's put the k here and do k minus 1. So I always think a little bit about notation. So this way, when I look at the distance from x1 to x2, it's at most 1/2 squared. What do you think the distance will be between xnk minus 1 and xnk?
So you can lose 1/k, third 1/k.
Not square root. What happens to the length of the subinterval every time we do another iteration? It started at 1, then 1/2, then 1/4. What's the next one going to be?
2 to k.
Yeah, so it should be at most 1/2 to the k.
Yeah, okay.
So we have a sequence of points where the distance between them is getting smaller and smaller and smaller. And so now what you need to do is you just need to do a little bit of analysis to show that this sequence has to converge. And so when you do analysis, you might see things like the Cauchy criterion. This is not an analysis class, so I have to resist my temptations to turn this into real analysis. My goal is to do enough to leave you with the sense that, yes, this is reasonable. You can see that this is going to work. If you want more details, I am happy to do more details. But every time we iterate, you're getting closer and closer, closer. We can also do a little bit more. What's the distance between xnk minus 1 and xnm for any m greater than k minus 1? So for instance, if we keep going, how far could something be from xn1? These intervals are all contained in each other. We had 0, 1, then we had 1/2, 1, then we had 1/2, 3/4, so they're all contained. So what's the furthest something could be from xn1? Good, and what's the width of the interval? It would be xn1 is in 1/2 to 1, so that would be 1/2. What's the furthest something could be from xn2? 1/4. So the furthest something could be, all right, so in fact, I don't want k minus 1, I want k. So the furthest something could be from xnk would be 1/2 So in terms of converging, if I look at the billionth term in my subsequence, then every other term in the sequence is within 1/2 If I look at the quadrillionth term, everything from that point on would be within 1/2 of that. And so hopefully this is enough to give you a convergence. If not, what you can always do is you can look at the left and the right endpoints of the intervals. We have nested intervals. We can look at intervals ANK, BNK. And then the ANs are strictly, the ANs are never going down, the BNs are never going up. So ANK is non-decreasing and BNK is non-increasing. And because the intervals are getting smaller and smaller and smaller by a factor of 2, what must happen to the left and the right endpoints? They have to merge. They have to hit each other. And since the sequence is always contained between the left and the right endpoints, your subsequence will have to converge. So this is how you would make it rigorous. You'd put in a little bit more detail here. But we have these nested intervals with the left and right endpoints approaching each other. The left endpoint never gets smaller, the right endpoint never gets larger. Okay, are people happy with this proof in the one-dimensional case? Now we need to do the two-dimensional case. So how should we do the two-dimensional case? I can think of 2 ways. How might you generalize the one-dimensional argument to a two-dimensional argument?
Instead of like the number line, we can use the square.
Good. And then what do we do to the square?
Divided into quarters.
And divide into quarters. So proof by picture, done. Right. And then at least one of these 4 has to have infinitely many. And then you would just lather, rinse, repeat. And then you would chop this up. I think I did red next. And then maybe the green is down here. And we would just keep going like this. So that's one proof. Here's the second proof. We have a sequence, X and let's call it alpha n, beta n. Okay. Get a subsequence X and K such that alpha and K converges to alpha. It's horrible alpha. Okay. So we have a new sequence that converges to at least the X coordinate converges. Do we know that the Y coordinate converges? No. So let YK equal X and K is alpha NK beta NK. We know alpha NK converges to alpha. But we don't know the betas converge. But if we're living in a square, the betas are all in 0, 1. What can we do now? Good, cut 1 in half. Yeah, so now apply the one-dimensional argument to the betas. And you would get a new sequence, YKL is alpha NKL, beta NKL. And you would just argue as before. So what we do is we first take a subsequence where the first component converges. And now we unfortunately don't know that the second component converges, not a problem. Just do it again. What if we had 3 dimensions? What would we do if we had 3 dimensions?
Just add a variable, expand space, and then make the same.
Yeah, so we could do either proof 1 or proof 2. Yeah, we could have a box and divide the box into how many pieces? 8. So the segment was 2, the square was 4, the box is 8. Or we could do the second argument, where we first pass to a subsequence where the first component converges, and then pass to a subsequence of that such that the second component converges, and then pass to a subsequence of that so the third component converges. Now, this is where tech is wonderful, where you can do things such as B sub n sub k sub L and actually have it readable. Years ago, I was working on a project with some people who were working in Microsoft Word, and I could not read what was a subscript or a subscript and whatnot. It was just, now again, this was also more than 2 decades ago. But it's really important to be able to quickly look and see what's going on. It's not so much fun to write this. The other thing is you could just do it once and say, look, if I have 3 dimensions, if I do it once, I now pass on to the 2-dimensional case, and by induction, we're done. So does this mean that if I give you any number of dimensions, it's going to work? So let's consider S is the set of all x equals x1, x2, dot, 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 such that x1 squared plus x2 squared plus dot, dot, dot equals 1. So this is the infinite dimensional unit ball. Does everyone agree that this is a bounded set? Can somebody give me a bound for this set? 1,
Yeah.
right? So it's bounded. Take R equals 1. Do you think every subsequence, do you think every sequence has a subsequence that converges? Or can you give me a sequence that does not have a subsequence that converges? What do you think? Does every sequence have a convergent subsequence, or if not, can you give me a subsequence, a sequence that has no convergent subsequence?
Well, like 1 plus -1 to the n.
Well, remember, we're squaring things,
Oh, right.
so it's too large. But I like your idea of, let's start off with the first point is 1 and then all zeros, because we know that's clearly in the set. Can somebody give me another point in the set?
0, 1, and then all 0.
This is an example of priming. By writing down the number like this is hopefully getting you to think in a certain way. What's the next one?
0, 2.
Yeah. So do you think every sequence has a convergent subsequence? If this converged, what would the first component have to be of whatever it converges to? Zero. What would the second component have to be?
0.
And we want the sum of the squares to be 1. So if converges, every component is 0, not in space. What's wrong here? What's the danger? Why is this not a contradiction to the Bolzano-Weierstrass theorem?
Because there's infinitely many.
Yep. infinitely many components. In particular, what can you tell me must be true about the set S? So if you look at the Bolzano-Weierstrass theorem, we know something must be true immediately about S. So what do we know about S? It's not closed. Why do we know it's not closed?
You have a sequence.
Right. We know that we have a sequence that doesn't converge. So the conclusion of Bolzano-Weierstrass fails. So the only way it can fail is one of the conditions must not hold. We show that the set is bounded. So it must be the case that it's not closed. So again, when you remove a condition, you get a much better sense of what's going on and the danger. Whenever you see infinity, infinity is always a warning that you have to be careful. And so in a finite dimensional space, this is not a problem, but you've actually seen infinite dimensional spaces before. If you looked at Taylor series expansions, you have your directions 1, x squared, x cubed, and so on. So you have worked with infinite dimensional spaces. It just hasn't been formalized. And you have to be careful. What's a beautiful rule about sums of derivatives? The derivative of a sum is the sum of the derivatives, right? You know, the product rule is not what you would want, right? The sum rule is exactly what you would want. But it's actually only true if we have a derivative of a finite sum. I'm not sure what happened. So if we have a derivative of a finite sum, then we might actually have some trouble. Then we have no trouble. But if we have a derivative of an infinite sum, then there is danger that we do not necessarily know that the derivative of an infinite sum is the infinite sum of the derivatives. You have to be careful. And so what I wanted to do in this part is just show you how careful you have to be when we do something like the Bolzano-Weierstrass theorem. It is true when the conditions hold, but there are some examples where the conditions do not hold, which if you're not careful, you may not notice, and you may try to apply it inappropriately. Okay. So, I guess what we really should do is then, I guess technically the application to the fixed point theorem. And I'll move this slide into the correct order. So technically what we have is we have the triangle 0, 1, 2. And let's say when we do our first subdivision, we got a triangle over here that had a 0, 1, 2 label. And then maybe when we did it again, maybe we got over here a 0, 1, 2 label and it was smaller. And then maybe later on, the next one was down here, 0, 1, 2. And then maybe the next one was in here. And so we have a sequence of these triangles. What must be true about the sequence of these triangles? What must be true about a sequence of those triangles? They must converge. So with the sequence must converge?
Yes, I would say well, the sequence because it's a closed set, right?
Imagine I keep hopping between a triangle very close to 1 and a triangle very close to 0. So I could actually give you, triangles like this and triangles like this. So we don't know that the sequence has to converge. So what do we know?
So each individual triangle itself converges to one fixed point.
Not each individual triangle. We have a sequence of triangles. If you want, specify the triangle by the location of the 0. What must be true about the location of the 0. That gives us a new sequence. Each triangle, we attach the location of the 0.
It's all bounded.
It's bounded, but what must be true about this sequence? It has to have a convergent subsequence, right? Must be a convergent subsequence. And what's the size of each triangle relative to the size of the previous? If we subdivide by doing an extra factor of 2, each one is half the size of the previous. Each triangle in the original sequence is 1/2 the size of the previous level. So we can look at the location of the 0, and that has a convergent subsequence. And so what's going to be happening? We're going to have this convergent subsequence, and we're going to try to evaluate f at this point where it converges to. So let's say we have converges to z for 0. And we know as we get these smaller and smaller triangles, what's going to go on? We're going to have z located over here. And maybe we have one triangle that's like this, labeled 0, 1, 2. And then maybe I have another one like this labeled 0, 2, 1. And maybe I have another one, coming down here, 0, 2, 1. I'm going to have some kind of string of triangles like this. Do I know that the triangles have to be inside the other triangles? No. I just know that there's a subsequence that converges. And so when I'm trying to think, what do we know about f of z? So let's call that f of x0, x1, x2. Well, we have a sequence of labels of 1 that converge to z. We have a sequence of labels of 0 that converge to z, and we have a sequence of labels of 2 that converge to z. Oh, wait, sorry. I don't know that they all have a common point. Sorry. So maybe here's my point z. Here's a 0, 1, 2 triangle. Here's another 0, 1, 2 triangle. Here's a 0, 1, 2 triangle. I'll put the 0 up there, 0, 1, 2 triangle. We have a sequence of zeros converging to z. So we have sequence of points labeled 0 converging to z. We also have a sequence of points labeled 1 that converge to z, and we have a sequence of points labeled 2 that converge to z. So let's think about what's going on. F of z is going to be something. Let's call it x0 prime, x1 prime, x2 prime. For every point which has a 0 label, that's the first index where it's strictly less than the input. So let's call these paths 0, 1, 2. So along 0, we have f of the point what must be true about the x coordinate? It's got to be less than or equal to the x coordinate of the point. Right? Because the label 0 means that's the first index, which is small. If you think about the original triangle, we start with a 0. Since this is not a fixed point, it has to be less than 1, so it got smaller. So along the 0, each x coordinate of the application of f has to be less than the x coordinate of the original. So if we take the limit, in the limit, the x coordinate of f of z has to be less than or equal to z's x coordinate. Right? It was technically, it's strictly less than here, not less than or equal to. So if we look at what's coming on from the zeros, it's strictly less than, strictly less than, strictly less than, but in the limit, it could be less than or equal to. Just like the sequence 1 over n is always greater than 0, but in the limit, it's greater than or equal to 0. But if we look along 1, what happens? Along 1, in limit, y coordinate of f of z is less than or equal to z's y coordinate. And then along 2, in limit, third coordinate of f of z is less than or equal to z's third coordinate. But remember, the sum of the coordinates has to be what? What must be true about the sum of the coordinates? Well, if I give you a point in my triangle, I'm representing it as, say, alpha, beta, gamma. What must be true about alpha, beta, gamma? They're non-negative. What else? They sum to 1. So if the x coordinate is less equal to z's x coordinate, and the y coordinate is less equal to z's coordinate, and the third coordinate is less equal to the third coordinate, well, if I sum all of these, that's 1. If I sum all of these, that's 1. So could any of these be a strict less than? As coordinates sum to 1, cannot have any less than, only equal sign. So z is a fixed point. So this finishes the proof that we actually do have a fixed point. And the idea was we have this sequence of triangles, and we know that it has to converge. So if you want, we could say, let's look at where the zero label converges. We could also look at the center of these triangles. They're all going to be equilateral. We could have said, choose the center of the equilateral triangles. Those centers have to converge. So it converges to some point z. And there are 3 different ways we can get to this point z. We can get to it along the zeros, along the 1 labels, or along the 2 labels. And if we look at it along the 0 labels, we see that the 0th coordinate is less than or equal to the 0th component. Then if we look along the 1 label, we see similarly it's less than or equal to, and along the 2 label, it's less than or equal to. But the trick is because they all have to sum to 1, if there was ever a strict inequality, we would have a problem. So we now know that it has to converge. So this finishes the proof of the fixed point theorem. And this shows how the labeling from Sperner can be used to get the existence of a fixed point. And now we can use this. So one of the things I want to do for the end of the semester is talk a little bit about some of the applications, or better yet, to allow all of you to talk a little bit about some of the applications. So I would like everyone to give a talk anywhere between 20 minutes an entire class on something related to operations research from anything in the book that we haven't covered. And so part of this is, if you are a math stat major, you have to do a colloquium. It's good to get some experience earlier in your career so that your first time is not when the chips are down and this is the talk that really matters. The other thing is, the more times you talk, the better. I have the videos from previous times I've taught this class online. You are welcome to look at videos of previous lectures and try to find a topic that you would like to do. And I'm happy to work with you on how do you want to present material. It is one of the most valuable skills to get, is how do you give a technical talk? And the kind of talk you give is going to depend greatly on who is in the audience. how much background can you assume from people in this class when you give a talk? Everything that we've covered, perfect. You can't assume familiarity with what you're about to cover. You could say, for the class that I'm doing, I want you to read the following pages in the book, or I want you to look at the following sheet that I'm preparing. That's absolutely fine in terms of, if there's some things you want people to know before you give the lecture. But sometime between now and if you want to give the talk either during reading period, or if you want to give the talk during exam period, that's fine as well. When you have a rough idea of when you want to give the talk, let me know. This also gives another data point that's non-exam. So it's another chance for you to show me what you're able to do. It's something that you can really focus on and prepare. When I need to write letters of recommendation, it also gives another data point for me to talk about. Some of the most successful students I've taught in operations research have been some of the worst students on the exams. But in terms of actually being able to present material, to interact with people, to form groups, and to have things accomplished, they are some of the best. And so a lot of what I'm doing is designed for that. Also, everyone should be writing a letter of recommendation for someone else in the class. This is a chance to give another data point for someone to write about. So one of the fun topics that somebody could do if they're interested is Nash equilibria. Of curiosity, has anybody taken a class that's done Nash equilibria? Okay, economics class? Okay. How much did they prove?
Like nothing.
Like nothing, okay.
Yeah.
And so I'll leave this for tomorrow, for Wednesday's lecture. We will do just a little bit of Nash equilibrium to just set up why we might care about this and how useful and how prevalent this is. I'm going to stop recording. Give me 1 second.